Okay, so welcome back to the lecture series on group theory. So in the last lecture we did discuss on several stuffs related to the subgroups. We also discussed some operations on the subgroup that we can easily do, making sure that the product of the operations will remain a subgroup again, and of course under some conditions. And also we have defined something called as cyclic subgroups. So as I promised last time, that though I told very briefly but didn't write it properly, is that something called a cyclic group. So what is a cyclic group? It is considered that G is a group, and if there exists some element G in capital G says that the subgroup generated by G, which is basically G power n, says that n belongs to Z, where G power n is defined as G times up to G. This is n times when n is positive, and it is identity when n is 0, and this is G inverse of G inverse times G inverse times up to G inverse, that is up to n times when your G, I'm sorry, not G, it is n is negative. Okay, so this is a cyclic group, and most common examples one can easily think of set of integers that is generated by 1 actually, right? In fact, we can have 1 and minus 1 as well. So you can take it as an exercise, or it is very easy to observation that if G belongs to G is a generator for G. So this particular element small g is said to be generator. So generator for the group G, then G inverse is also a generator for G. Okay, so that means if you have a G is a group, then you can consider a generator to be your G, or you can consider a generator to be your G inverse, making sure that G generates G, either G or G inverse, they generates the entire group. Okay, all right, and maybe we can define some other kind of groups, that is basically let G is a group and we consider S is subset of G, which is of course non-empty. Okay, then let the class of the group, this is C, is basically of the form H is subgroup of G, such that H is a subgroup such that S is contained in H. So we consider all the subgroups of G that contains this particular subset S, and of course we may consider S is non-empty. Okay, so then if we take the intersection of all the subgroups, so of course it's a subgroup, right? Because we have already seen that any finite or infinite or countable or uncountable intersection of subgroups is always a subgroup. So is subgroup of G, and of course S is inside this intersection. So this particular subgroup is said to be subgroup generated by S. Okay, so that means more precisely this is the smallest subgroup of G that contains S, and of course S as a subset. Okay, so you can easily determine that if S is itself a subgroup of G, so this will readily imply that the subgroup generated by S, okay, so we usually denote it as in this way, there is subgroup generated by S. So if S is itself a subgroup, then the subgroup generated by S is basically S itself. Alright? Okay. So there is a theorem that says that, so let S is subset of G and S is non-empty, then the subgroup generated by S, which is basically denoted in this way, is basically is a set of all the elements of this form, which is basically x1 times x2 up to xn, such that n belongs to natural number and for each I from 1 to n, either we have xi is in S or xi inverse is in S. Okay, so that means it is a set of all the finite products of the elements x1 to xn such that this particular property is satisfied. That is, either we have xi is in S or the inverse of xi is in S. Okay, so the proof is pretty easy. We don't have to do a lot of headache here. So just make sure that you have understood the structure of S, the subgroup generated by S, so which is basically the smallest subgroup of G that contains S. So this is the key idea to relate the subgroup generated by S with the given set that we have got here. Okay, so let us consider that we denote it as M, basically set of all x1, x2 up to xn, such that either xi is in S or xi inverse this is in S for all n belongs to natural number. Okay, now we choose any two elements from here. So let's say A is basically of the form x1 up to xn and B is basically of the form y1 up to ym. Okay, so these two elements are there from M. Alright, now what we can do that if we take AB inverse, so AB inverse means we have x1 up to x2 up to xn times ym inverse, ym minus 1 inverse, so on up to y1 inverse. Okay, so then we basically get, now note that once we have xn times ym inverse, so now let us consider xn belongs to m and ym, this belongs to m. Okay, so either you have xn is in m or xn inverse is in m. So here again we have ym is in n or ym inverse is in m. So if you now see that we have the here finitely many length of finitely many elements here, and we have here finitely many elements. So for now, if we just go point wise, we basically get that, let us take x1. So if we take x1, then if we have x1 is in m, s or x1 inverse is in s. If we take x2, so either we have x2 is in s or x2 inverse is in s. Similarly till up to xn is, it is true. Now for ym inverse, so since ym is a element, I mean is a point of or a coordinate point for b, so basically with either we have ym is in m or ym is in s or ym inverse is in s. So yeah, this will be s, not m. So now if we have ym inverse is in s, then we are done. If we have ym is in s, that will imply ym inverse whole inverse is in s. So that means we can rewrite these terms as something zm, zm minus 1 and z1. Okay, so now you can easily visualize that this particular condition, that this particular condition is basically readily imply that AB inverse is basically inside your subgroup generally S. So that means, okay, right now not subgroup generated by S, just let us stick with M, because we have not proved at all that it is a subgroup. Rather, we are just trying to prove it is a subgroup. Okay, so that means M is a subgroup. Okay, now since M is a subgroup, then what we can take for all small s in capital S, we can just take a word of one alphabet, that is S. So of course S should be there in your M. So that means M is a subgroup that contains S. Okay, now converse, now again let H be any other subgroup of G such that H contains S as subset. So now if H contains S as a subset, then of course for all X belongs to S, we have X belongs to H, and as well as X inverse belongs to H. So that means for any x1 up to xn belongs to M, what do you have? That either x1 is in S or x1 inverse is in S. So for any of the cases, either x1 will be in H or x1 inverse will be in H. So for any of the cases, we can get that each of the elements x1 or up to xn, that will be there in your M, right? Because if x1 is there, I'm fine. If I have x1 inverse in H in S, that means x1 inverse is in H, so I'll be taking the inverse of x1 inverse, that is here again x1, and thus for each xi I can follow the same procedure. So basically we can get that your M is contained in H, and this is true for any. So that means we have that M is the smallest subgroup of G such that H contains your M is the smallest subgroup such that M contains S as a subset. Okay, hence your M is nothing but the subgroup generated by your S. Okay, so this is a way how to characterize the subgroup generated by some set or some subset of a subgroup of a group. Okay, now let us move to some other very important stuffs, that is something called the cosets and the Lagrange's theorem. Alright, so suppose that G is a group. Now let small h is a subgroup of G. Okay. Now, so this is your group G, and let's say somewhere here is your subgroup, it's your H. Now we define so relation on G such that for any two elements G1 and G2 in capital G, we have G1 is related to G2 if and only if G1 G2 inverse is there in H. Okay. Now you can easily check that this relation is basically equivalence relation. So like the check is basically very straightforward, that is the reflexivity. The reflexivity is basically given by, let's say, G belongs to G. So G inverse is 1 that belongs to H, that is identity element is in H. And so of course G is related to G, right? So that is basically gives that the function is reflexive. Alright, now since it is reflexive, so you can now check that the symmetricity, that is symmetricity. So let G1 is related to G2, right? So that means we have G1 G2 inverse that is in H. Now since G1 G2 inverse is in H, that means the inverse of this G1 G2 inverse has to be there again in H. So this will imply that G1 G2 inverse whole inverse that has to be there in H, which means G2 G1 inverse is in H. Hence we have that G2 is related to G1. So that means whenever we have G1 related to G2, that implies G2 is related to G1. That means it is symmetric, right? And the final one that you need to check is transitivity. So transitivity is basically given by, let us consider that G1 is related to G2 and G2 is related to G3. Okay, so then G1 G2 inverse and G2, G3 inverse, that has to be there in H. So now what we can do, we can multiply this one and this one. Okay, so that means G1, G2 inverse, G2, G3 inverse has to be there in H, which means that G1, G3 inverse is in H. Hence, G1 is related to G3. So that is basically given by the transitivity. Okay, so that means the relation is equivalence. That means whenever G1 is related to G2, if and only if G1, G2 inverse is in H. Okay, that is this particular relation. So this is a equivalence relation. Now since it is an equivalence relation, so then we can just make a partition of G with respect to the equivalence classes. So the equivalence classes will be of this form. Maybe you can just take the partition like this. This is the equivalence class. This is the equivalence class. This is the equivalence class. This is an equivalence class. Similarly, this will be an equivalence class. This will be an equivalence class. This will be an equivalence class. So the number of equivalence classes can be finite or can be infinite as well. But our main concern is that how the equivalence class will be looking like. So the equivalence classes, so let us consider of, let's say, class of some small g in capital G. So we just take as particular elements small g and we take equivalence class of that. So this equivalence class of G is basically set of all small h in G such that G H inverse is in H. Let us not take H. So set of all Gx belongs to G such that G times X inverse is in H, which means X is in G such that G belongs to H. Okay, so that means G of times X inverse, this should be as a form of small h, right, for some small h from capital H. So which means that we can write G to be as Hx for some h, right? So that means the equivalence class of G is nothing but basically of the form h times x. So Hx is basically defined as Hx such that h in capital H. Okay. Wait. Okay, not maybe like this, but okay. So I need to characterize small x. So okay, instead of writing in terms of G, let us write x to be as H inverse G, right? So that means small h inverse is belongs to capital H, right, for some h. So the equivalence class of G is basically nothing but Hg, or H is basically defined as small h times G such that small is in capital H. Okay, so this is how we can make a partition for the entire group G. So these are called the right cosets for G. And similarly, so another kind of binary operation, for example, if we consider an equivalence relation that is maybe tilde on G cross G such that, so it is tilde such that for any G1 comma G2 belongs to G, we have G1 is related to G2 if G1 inverse G2 that is in capital H. Okay, so if we consider any equivalent situation like this, so that means we have just changed the position of the inverse here. So in the last time, I mean, for example, here we considered the equivalence relation in such a way that the inverse of some element that is the right one at the right side. But here we have just multiplied G2 with the inverse of some other element from the left one. So in this case, the equivalence classes, so one can easily check that this relation is also equivalence relation. In fact, you can consider it to be an exercise as well. It's not a very hard one, but the same procedure that you have followed here. In fact, that is a mirror image of that, nothing else. So basically, if you consider the equivalence relation on G in this way, so then your equivalence classes will be given by something of the form G times H, right? So these are called the left cosets. Okay, so now so that means we can partition G either in terms of the left cosets or small g in capital G such that it is of H. Note that if we have G to be a abelian group, in that case your left coset is same as your right cosets. Okay, all right. Now but all the time the left cosets and right cosets may not be same. Okay, all right. So we may call that this left cosets or whatever be that to be cosets based on the position that is either left or right. So these are the cosets generated by small g or represented by small g. Okay. So that means we can make the partition for G in this way. So then the cardinality of G is basically summation over small g in capital G mod of G times H, or summation over small g belongs to capital G is mod of H times G, cardinality of each of the equivalence classes, right? Now what are the so now okay, so basically this is the general structure. All right, now if you consider that let your G is finite, so that means you have H is also finite. Okay, so then we define phase mapping from GH to H such that small phi of G times H is basically of the form H. So is it a well-defined function? So your well-defined is basically given by, let's say, G times H1 same as G times H2. We can multiply G inverse for in both the cases from the left side. Then you can get that H1 is same as H2. Right? So it is well defined, is there. In fact, if you consider, let's say, phi of GH is same as or phi of GH1 is same as phi of GH2, that will imply that H1 is same as H2. So which means that G of H1 is same as G of H2. So that means it is injective. Okay. And for the others, for the surjective one, let small h is in capital G, then we have GH is in small g times capital H, then phi of GH is your H. So it is surjective. So since it is surjective, then we can get that the cardinality of mod of GH is basically same as the cardinality of mod H. Okay, and we have assumed that to be finite. Okay, so then which will imply that mod of G is basically same as small g belongs to capital G times mod H. Now how many cases it will be there? So basically the number of index, so how many GH are there? So basically the index is basically the number of index is basically the number of equivalence classes, which is basically mod of G over H, right? So it is basically the number of equivalence classes. Okay, so now the number of equivalence classes is basically mod of G times H. So basically we can get here that it is mod of G times H times mod of H. Okay, so that means we basically get that mod of G over H is same as your mod G over mod H. So this is your Lagrange's theorem. Now note that we have said that, that was a motivation for study behind the Lagrange's theorem, is that when is always true that any subgroup, the cardinality of a subgroup will define the cardinality of G? The answer is yes, because the number of equivalence classes is basically finite. So, and in fact, it's a natural number. So that's why your mod G over mod H has to be a natural number. So that's why you can easily say that the cardinality of any subgroup will of course define the cardinality of the group of it, and in fact it's given that the group is a finite order. Okay, so this is a Lagrange's theorem, and that really plays a very vital role between the cardinalities of a finite group and its subgroup, and that will basically give birth of some more concepts related to something called the quotient groups and all. Okay, so let us stop it here, and I hope that you will be have a good revision with all those things. And in the next lecture onwards, we'll see some more properties of cosets, and of course there is a great question that whether the converse of Lagrange's theorem true or not. But it is true for some of the cases that we'll be discussing in some more within some more lectures. So okay, so thank you very much for your attention. Let's stop it here.